we are recording. If for any reason that this little symbol up here, that little recording sign, goes away, just yell at me. Because that happened the last time, and I would rather not have this review session get cut out midway. Anyway, so we're doing the network layer and the transport layer. Fun stuff. So let's get started with some of the short answer questions. These will definitely be on the exam. I mean, obviously not all of them because there's a lot of them, but he'll just probably pick a couple and go from there. So let's kind of take a look at those and go from there. So why is it not possible to build a global network such as the internet using link layer L2 switches? We learned L2 switches are not scalable. We cannot scale with this because the link layer is not compatible with all different types of local access networks, LANs. So we need a router to be able to communicate with all different types of these L2 layers in a sense. So you can think of it as like the translator between everything. Okay, assume that the net mask for your network is 255, 255, 128.0, and your IPv4 address is 23.45.65.66. What's your IP subnet? How many hosts can you connect to on your IP4 subnet? Okay, so anytime that you see 255, 255, right, we know that these first 2 bytes are going to be our subnet, right? So because of that, we know that the subnet is going to be 23, 45, and then these guys are zeros. So because of that, right, how many zeros do we have? Well, each of these guys is a byte, right? So we know that if we were to bitwise AND this with this, right, we know that obviously the first 2 are zeros, and then we have to see with the third bit which bits are currently taken. And we do that by doing the bitwise AND operation. So we see that this is 128 and this is 65. And with bitwise AND, if there's a 1 in both positions, the answer is a 1. If there's a 0 in one and a 1 in the other, or both zeros, then it's 0. So it has to be both bits in the same position. So in this case, right, we see that we have ourselves 0, all zeros all around. So that is just going to be our 2 zeros there. And we see that because of the net mask, right, we see that there are 7 zeros here, right? And then there's another byte that we're missing because this is just dealing with the third byte. So because of that, right, we know that there's going to be 7 bits in the third octet, or third byte, whatever you want to call it. And this byte over here is going to have another 8 zeros, right? So this is kind of like what the last 2 bytes of the our net mask is going to look like. And that's kind of telling us, okay, I have these guys, and the formula that we know is 2 to the n minus 2 hosts. So how many zeros do I have? Well, I have 7 plus 8, which is 15. And I know that's going to give me 2 to the 15, right? Because each of these can be a 1 or a 0. So this could be a 1 or a 0, 1 or a 0, 1 or a 0. If you wrote this out, you'd literally have 2 options, 2 options, 2 options, continue, continue, continue. Think back to probability class. And then you minus out 2 hosts. So the ones that are all zeros, so if all 15 of the bits were 0, that's kind of just referring to your subnet. They call it like the this subnet. And then if they were all 1s, that would be a broadcast. So the formula here, which I think I wrote it kind of further down when there were more of these questions, is when you have here. host is always equal to 2k minus 2. So we minus the broadcast and the this IPs. So this is always the key to remember. If they ever ask a question on how many hosts there are, right, how many hosts can connect to it, you just kind of want to see how many of these zeros are available. So this is a question that will probably appear. He kind of went over it, like, oh, how many hosts can I make if I divide this into 4 subnets? There's more questions on this later on, so. Okay, let's continue with the short answer. So what would be the disadvantage to placing...
Excuse me, I have a question.
Yeah, absolutely. What's up?
So back on that where you said the IP subnet and the how many hosts you can connect. So I know you got the 128. Like I know you got that like the 1 and then 7 zeros from the net mask, and I know you got the following line from the IP address and you do the bitwise and you got 23.45.0.0. That's the IP subnet, right?
Yep. So this is like my answer to 1, and then this is my answer to 2.
Okay, so my question is like, you know how you have the 128? How'd you get the 8 zeros next to it? Is it just from the net mask?
Yeah. So this is...
Oh, and then okay.
Yeah, so I just didn't include the 255 for the net mask because obviously those are just going to be 8 ones, right, for 255.
Right.
So all you need to know is that you're looking at these guys over here because your net mask ends after this last bit, right? This 128 is saying that this 1 is part of your net mask. All of these bits are your host bits. And that's how I got the 7 plus 8 host bits and plug it into the formula, and that's the number of hosts.
And then the number of hosts is 2 to the k, which is, and k is the number of zeros, minus the 2 because the 2 are reserved, like the broadcast and this is all zeros, that those 2 are reserved, right?
You got it.
And then just the number of subnets is just 2 to the k, but no minus 2.
Exactly. Yeah, I think I have the formula somewhere around here.
Oh. Yeah, you just showed it, I think. I'm just making sure. Oh, there you go. All right, perfect. Thank you.
Okay. I'm gonna make that red so I can see it clear. Yeah, for any of these questions, usually like I try to put the rule in there too, because like if you know the rule, then you should be good. Yeah, we'll go through a bunch more of these. He gave like I think 6 of them like this, so there's a lot to practice with. And by the way, everyone else stop me if you have any questions, so go right ahead. Okay, part C. What would be the disadvantage to placing the IP version number in a place other than the first byte of the IP header? So, you know, we have 2 IP versions, right? V4 and V6, and both of these guys have very different structures. So if we don't place that in the first byte, how are we supposed to parse through the rest of it? And that's kind of like what I'm saying here. You'd have to parse for the IP version before parsing the IP address itself, since you must know the IP version to know the lengths. It's as if someone gave you a sentence in some language you don't know, and at the very end, then they tell you what language it is. So it's like, how are you supposed to decipher this if you don't even know what language it is? Like, maybe you can decipher it on your own, but for the most part, your IP number should always be in the first byte.
And IPv4 is 32 bits while IPv6 is 128, right? Is that it, or?
Yes, that sounds about right.
32. Okay, 32 and 128. All right. Thanks.
No problem. All right. Part D, give a network application that would be better suited for a datagram-based network than a virtual circuit-oriented network, and a network application that would be better for a virtual circuit-oriented network than a datagram-based network. So we learned about these back in Unit 1. So virtual circuit is going to be a fixed path. So because of that, you're always going to have it being ordered and it being reliable. But it's not very, it can be very wasteful if you don't have the same number of data in your bit stream in a sense. So like if you're reserving all of that bitstream, like all that circuit that you set up, and you're sending like a tiny little message in it, it's very wasteful. Enter datagram based, where we're doing different packet sizes. And these we could kind of change based on how big it is. So usually, like datagram would be better if like you're sending a text message out or doing video streaming. So like video streaming is usually very like the kind of I guess like the ideal answer in a sense, because also you could afford for packets to be out of order and you can deal with varying sizes. You want it to be very fast, right? So you want the video stream to be fast. You don't want it to be buffered or anything. But if 2 frames were like slightly out of order, like the usually you can't really tell because what is it like? It's 24 frames per second, right? Our eyes can't really tell between that so much. So because of that, this is better for datagram, or even a text message is honestly good, right? You want things to be like super fast when you're sending out a message, right? If you're just saying like hi to someone, you don't want that to be taking forever. And even though maybe virtual circuits is, you're always going to have it in order and it's going to be like quality of service and stuff, it takes longer because of that. But one thing you do need in order is a telephone network, because otherwise that would be extremely weird if someone's message ended up kind of appearing all like jumbled up. It'd be like a lot of
Hmm?
like feedback that you get back from that.
Would a better example of datagram be like text messaging or like no?
Text message could work too.
Like,
Yeah.
because when you text someone, it's like if it's like a big message, like all the packets, it's gonna be fragmented into packets because if it's a big message, and like if it's sent out, I assume like at the end, like if it takes like a second, when it at the end when it reconstructs it and displays a message on the other side, it's like, uh, yeah, like is that how it works or
I'm sorry, just repeat yourself again.
like in datagram when it splits everything up and then sends it out on the network and then at the end reconstructs it? That's how like datagram works, right? Or
Yeah,
no?
exactly. Because it's like it's going to be out of order,
Okay.
right? Like you can't really guarantee the order, and it just reassembles itself at the end. And sometimes you lose packets midway. Um, so yeah, the only thing is there is like that out of order aspect that is a little worrisome, because like if someone sent the message like hi, how are you, and then it came back the other way around, how are you, hi, it's a little bit different than with videos, because like you're able to have a lot of different frames here. So it's like if one frame comes before another one, it's much less noticeable than if you had like with text messages in a sense. So if that makes sense. Okay. So we continue talking about virtual circuits. Is it possible for 2 packets to arrive out of order? This is a big no, because again, virtual circuits has a quality of service. It is guaranteed the second you create that channel, that bitstream channel. So you are always guaranteed for it to be in order and to have a constant time for arrival. So constant doesn't always mean fast, but it just means that it's kind of guaranteed at that point. Okay, the internet is running out of IPv4 addresses to assign, but there are substantially less than 4 billion hosts on the internet. Briefly explain why this is happening. This is due to a magical thing called NAT, the Network Address Translation. And this is kind of like a way to almost like mask your IP in a way, in the sense that you have private IPs and public IPs. So your router at home is one public IP, and it will assign multiple private IPs to all of your devices, your laptop, your phone, etc. So, multiple routers, they'll have different public IPs for sure, but their private IPs can be the same. So, maybe someone's phone has an IP of 10.10.10.10, and someone else's iPad has an IP of 10.10.10.10. That's totally fine because of the network address translation. Um, and this, as the name suggests, translates for the devices that are connected to it with its own reusable private IP addresses. So they can totally reuse the IP addresses in there, but the key is you want to make sure that you only have the public IP address, which is the ones that are registered with like the internet service providers. Those got to be with the routers. And I think there's a question that talked about what the benefit of this is, and it, number one, addresses the lack of IP addresses, and also it's a security thing too, because now no one can route to these private IP addresses, so you don't have to worry about like someone trying to hack your IP or something. I mean, unless they're on the same network, but that's another story. Anyway, what is CIDR? Classless interdomain routing. So we have two things, class full addressing and classless. And that should not have moved. Oops. So class full is the one that allocates the address ranges based on like the first couple of bits, right? There was one that was like, if it starts with 10, it's an A address. If it's 110, it's a B address. Continue on and on and on. So with that, right, it's kind of wasteful because you're pre-allocating them. What if you need more of class A, but you can't because there's class B that's taking up that row? So with CIDR, we are able to essentially have that like .x bit, and that .x bit at the end kind of tells us how many bits are going to be allocated to our net mask, right? So you'll see the structure as ABCD/X. So sometimes this will be like 24, 23, 25, somewhere in that gambit. And that's just kind of saying that those first X bits are going to be for your net mask. So this is helpful for later questions because you'll see it in this format and you'll be like, oh, look at that. The first X bits are going to be our subnet. Okay, so we have H, the IPv6 header is 40 bytes long as opposed to 20 bytes of the IPv4 header, while the address size has quadrupled. What functionality has disappeared from the fixed header? So there's a couple of different things, but the most important thing I'd say is probably the checksum, I think, and also the header length. So with the checksum, right, we kind of spoke about it, how it's kind of redundant. It was originally done because not all link layer protocols did it. I mean, Ethernet, that's just the standard, does like checksum and CRC, so we don't have to worry about that right now. But because IPv4 kind of like was brought on the fact that like it was like created to have that extra checksum in it, it kind of just continued with it. But IPv6 was like, no, this is wasting space. We're creating a new protocol. Let's have more bits for more important stuff like the data, and we don't need checksum. We also don't need the header length too because we make it fixed. IPv4 is not fixed, so because of that, it could fluctuate. This just says, okay, straight up, it's 40 bits. So because of that, it kind of makes things a little bit easier when parsing. As for other stuff, fragment offset. So when we were doing fragmentation, which is going to be like some other questions that we're going to be doing, it tells us like how many like the fragmentation, what its offset would be. And so because of that, the sender is not going to be doing the fragmentation anymore. So the key is, we make it a little bit longer. We make the size a little bit larger, right? So hopefully we don't have to like fragment it as much. So if anything, the fragmentation is done by the network, not by the sender. So we don't really need this fragment offset to be sent to us anymore because we're the ones doing the fragmentation. So as it was said before, IPv4 versus IPv6, 32 bits versus 128 bits. And what is an IP subnet? The subnet is part of the address that tells you what sub network you are on. So those are like the first couple of bits that are kind of referred to usually if we have like that slash x like we had up here. And it'll organize your networks. So if you have, I know with in class we kind of went over like, oh, the CS department has its own subnet. The biology department has its own subnet. Because you wouldn't want to have every single department at QC having the same subnet. Like, that would be extremely disorganized. So then we have the interface ID for IPv6. So we have two, because we have 128 bits, it's divided into two. The first 64 bits are the subnet prefix. So just like kind of with IPv4, right? Except the bits are not fixed with IPv4. But we know that the first X bits would be the subnet prefix. In this case, that's the first 64 bits. And with the last 64 bits, this is the interface ID. So this is kind of like your host ID. And what it does is it identifies the specific network interface, aka the host, on a subnet. So instead of being more like this structure with like IPv4, IPv6 is more like 64 for the subnet and 64 for the host. So, kind of makes things a little bit more easier to kind of see. So this was going back to private versus public IP addresses. There's a lack of enough public IP addresses, right? That was the whole situation. And then also security reasons, because you can't route to private IP addresses from the public. So these are the two main perks for the network address translation. So these are like the two main reasons for if either the question asks for that or if you have private IP addresses. What is a link local IPv4 address? So this is automatically assigned, right? So even if you are dealing with something on the same network, you will have an IP address allocated to you. And this is kind of like your default if you don't have like an actual IP address. So in case, let's say you're sending something to someone else on the same network, right? You still need to go through the network layer, but you'll have the link local address. And this will just allow you to use your link layer protocols really to talk on the same local LAN network. So that's just kind of automatically assigned to you, so you don't have to worry about if you don't have an IP address or if someone's on the same network, like you don't really need to go through the network layer at that point. But this is kind of like the way around that in a way. Okay, then we have a loopback IPv4 address. So this one over here is meant for testing purposes. It loops back to the user, to the host. So because of that, is it possible for a packet to be sent for it to leave the host? This is a big no, because this is local only on the host, right? Hence the name loopback. Anything that you send just loops back to your host, so you will not have any packets leaving the host and being sent to the network. Explain why IPv4 does reassembly at the destination rather than at the routers. So instead of waiting, instead of not waiting, I guess, and assembling them right at the routers, right? This is not always the best way of doing it, because if you lost one of your IP packages, right, in transit, our whole message ends up getting discarded at the routers, and this ends up wasting a lot of time. So if we just kind of continue continue the process and just kind of push it to the next layer, to the next layer, to the next layer, we end up with what's called independent packets, which are reassembled at the destination. You get to kind of think of like you're cramming all of your stuff into one box, so it's a little bit easier to kind of deal with shipping. This also makes things go a lot faster because your routers are only doing one thing. They're forwarding packets. They're not like reassembling the packets as well, which would end up taking a lot longer This allows them to go a lot faster. And instead of having to, stop and inspect every fragment, put them together back at each hop, that takes way too long. So this ends up making it go a lot faster. And in the end, right, it's better if we have our package treated as independent packets and they just go together, even if they end up in different orders or anything, they'll go back to the same destination in the end, and the application can deal with that at that point. Okay, so we have the difference between IPv4 and IPv6, handling passing packets through subnetworks with maximum transmission units. So sometimes you might end up with a bottleneck where your MTU at one link ends up being smaller than what your original link was, right? So it kind of ends up looking a lot like a bottleneck. So with IPv4, if the next subnetwork or the next link has a smaller MTU size, the routers are able to refragment the packets further with IPv4. And we're going to do an example like this. And this ends up making the sender's job easy because they're the ones that don't have to fragment it. But the router has to work harder, which takes up a lot more time, right? And you're going to see later on when we do those problems why it takes up so much time and how IPv6 might have the right idea in that it doesn't allow fragmenting at the routers, which just, so if they end up getting a packet that's too big, they just straight up drop it. Like, nope, this packet is way too heavy for me. Not dealing with this today. It's not my problem. You send it back to the sender, and you just tell them that your packet was way too big. So it's the sender's job now to make the packets smaller. Think of it as like it's Amazon's job to make their packages smaller so their delivery workers don't strain their backs. This allows our routers to work faster and efficiently. So it's kind of a trade-off here. So, are you going to do the fragmenting at the sender, or are you going to do the fragmenting at the routers? Somewhere it has to happen. So, either way, you'll either make the router's job easier or harder. That's kind of the same thing here, right? IPv4 can be fragmented at the routers, so this happens in between the hops. IPv6 cannot. It has to be done at the sender side of things. Otherwise, it's going to just drop it, just as we kind of said before. What is an IPv6 anycast address? So this is a single IP address that's assigned to multiple devices. So if, let's say, you assign everyone at Queens College a certain role, let's say, and they're like a representative. So when you send your packet to one, when you ask them a question, the person closest to you is going to be the one to answer it. So anyone can choose to accept this message in a way. And this kind of allows them to kind of be fast with this. Okay. IPv4 checksum, which is computed over the IPv4 header, is used to protect IPv4 header against bit errors. Why did IPv4 remove the checksum from its header? Well, first things first, the link layer was already going to be doing this. So what is the point of doing this again? The lower levels, like Ethernet, we're already going to be computing it. So why are we going to compute this again? We should just be able to do this a lot faster. And that's why IPv6 was just like, let me just get rid of this completely. Because again, it's a new protocol, so it can kind of change its way of doing it. IPv4, it's kind of set in its ways, so it can't really change things up right now. But if they're starting clean with IPv6, let's just get rid of that. Let's make it go faster. It's redundant. At this point, Ethernet's the standard anyway. So ICMP, Internet Control Message Protocol. And this has two main purposes, right? You're going to be able to detect if hosts are unreachable by pinging them. So these are echo pings, and you're kind of just asking if the host is alive or not. So, hey, are you alive? hey, are you alive? And if there's an error, right, your person, or well, your host would not be responding because they would be dead. So they would be unreachable. So this allows us to determine if a host is live or not. This is also used to see how many hops that we have between uh, like two different hosts as well. This was like that whole like time to live field, right? You kind of just ping back and forth, and every time you do a hop, it's like your time to live decreases by one, and then you kind of report back to see how many hosts are in between. And then you can kind of adjust accordingly. So it's kind of like a counter that you do. And doing these echo pings essentially allows you to kind of go through that and just see if those hosts are alive or not. Is it required for a node to join a multicast group to be able to send a packet to that group? So the key here is anyone can send to the group, but only those in the group can receive. So it's like you have to join the club to receive mail from them, but anyone can send mail to these people. Okay, almost there. What is the purpose of IP multicasting? So we have unicast, multicast, and broadcast. Unicast is one-to-one, broadcast is one-to-all, multicast is in the middle, one-to-many. So you could send multiple addresses at the same time. And you don't have to broadcast to everyone. So why are you going to bother everyone? Go through all of that bandwidth to kind of send it to everyone when you could just send it to a smaller group. What is the range of IPv4 multicast addresses? So these are your class D addresses, and they start out with the 1110 prefix. So these are like the different classes that we kind of went through. We had like class 1, class A, class B, class C, class D. And if you wanted to write these out, right, it's having the 1110 with all zeros to the 1110 with all ones. So that's kind of what that's saying. Okay. Explain how an IPv4 multicast IP address maps to an Ethernet MAC address. What is the MAC address prefix used for IP multicast? So there's a formula for this. It's 01005E plus the last 20 bits of the IP address. And this will give you a multicast MAC. So if it came to, I think there was like a question. Oh, actually it was right here. What is the destination MAC address of an IPv4 packet sent to this IP address? So first, convert this guy to binary. That's this over here. Sorry, did someone say something? Sorry, I haven't been taking a look at the chat. Question I should have asked earlier, but basically one broadcast domain, a subnet, and a LAN can house multiple of these subnets. So it's more of they could host multiple hosts. So you could think of like a subnet as like an apartment building, and the people that live there are your hosts. Okay, guys, let's keep it on track here. Honestly, yeah, let's get back to studying. Okay, I guess a lot of people joined. Welcome. Oops, one thing. Okay. Anyway, yeah, I guess if you guys have questions, just let me know. But let's get through this question over here. So we write this out to binary. Anytime that you see an address, you probably should write it out into binary first, just to really be able to see what's kind of going on here. For instance, you see 227, 23, 245, 2, and it's like, okay, this is a normal-ish address, whatever. What's the big deal? You write this out in binary and you see, oh, look at this, 1, 1, 1, 0. First 4 bits tell us this is a Class D address, right? It's within this range. It starts out with this prefix here. So that means that this is going to be a multicast. It's going to be a multicast packet that's going to be sent, right? So immediately, if we have to find a MAC address for this, we know that the first part is going to be this over here. So by default, we're going to have the 01, 00, 5E. And then the rest of it, the last 23 bits are going to be converted into hexadecimal. Right? MAC addresses tend to be in hexadecimal. And the way we do this, right, is by powers of 16. Sorry, just have a bit of a cold. But yeah, so we have ourselves the powers of 16 here. And this kind of just allows us to convert between the two. So if you don't remember hexadecimal conversion, this is probably a good sign to go over that. But the good part is it's only going to be 23 bits that you have to go through, right? Because these bits are going to be already defined for us, right? These are always going to be in front if it is a multicast address. So if those 4 bits are this, then we know it's going to be multicast. So always use that formula if it is multicast. And compare and contrast, multicast, unicast, broadcast. We kind of went through that. One-to-one, one-to-many, one-to-all. And again, you know, if you know who you're sending to, just unicast or multicast them. But if it's going to be everyone or you don't know who they are, then you got to broadcast. All right, then we go into intradomain versus interdomain. So intradomain, this is inner. So this is within an autonomous system. An autonomous system is just a word to describe a system that's kind of running on its own. Like you could think of like Queen's College, right? It's its own organization. And then interdomain is between domains. So that's going to be between these autonomous systems. So you could think of like Queen's College versus Queensborough College. And each of these has its own purposes. So if you're intradomain, you want to care more about finding the shortest path between 2 nodes on your same network. And these are usually through like using Dijkstra's algorithm or the, I think it was like OSP, like open shortest path first algorithm. Basically, like you just want to find the shortest path. On the other hand, if you have interdomain, you care more about routing yourself, hint hint, router, to your next network. And this allows you to exchange your routing information to find out which host lives on which subnet. So it kind of just is like, hey, does so-and-so go to Queen's College? Great, let me route that information to them. And then lastly, for the short answers, what is the count to infinity problem in distant vector protocols? How does RIP solve this problem? So when we have routers, right, we could essentially use the TTL, the time to live, to kind of find out the hop count between these 2 routers. And if we send incorrect information between the routers, like maybe I say, hey, router B has the answer, no, router A has the answer, no, router B has the answer, and we're going back and forth, my time to live counter just keeps increasing. And when I have to route back to this, I'm having like an infinite loop. I have an infinite string that is essentially counting to infinity. And RIP is the Routing Information Protocol. And what this does is it establishes a max hop count. So after that time, uh, it stops, and we use our friend ICMP to ping, hey, you timed out. This host is unreachable because it clearly should not have taken that many hops. Okay. So those are our short answers. And if you were to take a look at the short answers here, right, it's pretty much literally the same exact questions. Give 2 reasons why it is not possible to build a global network on link layer switches. Oh, look at this. It's the same stuff. Over here, same thing here. What disappeared? Oh, look at that. We discussed that. Checksum. IP fragmentation. Same stuff. Discuss why IP multicast is more efficient than broadcast. Again, we kind of went through this. It disturbs less hosts if you're doing multicast, right? Why are you going to broadcast to everyone if it's just something small? Probably there's going to be more than this amount of short answers. I would assume it's probably going to be like a lot of smaller ones. But these are probably going to be the more important ones, like all the ones here. And it's a lot of practice on the practice questions. So anyway, any questions? Okay, guys, let's kind of stay a little bit quiet with the commentary on clubs and stuff. Let's try to keep it more about networking. It's okay, things happen. All right. Any questions before we get started on the next part? There's a lot of network questions. So honestly, I'm trying to think of a good midway point to probably take a break in. Yeah, there's a lot of these questions. All right, let's try to at least get through these number of subnet questions. And then probably these tables too would be good to get to. So maybe if we could get to like... Yeah, okay, let's get to about question 13. I think that's like probably like the midway point in a way. Because the transport layer stuff, like there's literally not that much. So really this is the bulk of things. So anyway, let's get started with that. Do you think we'll get through everything tonight? That's the goal, honestly, because once I finish this, I'm going back to numerical methods, and I'm not looking at this until Monday night. I'm probably gonna not necessarily do every single question. Like, he gave us, like, 6 of these. It kind of gets repetitive after a while. So maybe I'll only do, like, half of the ones per rule in a way. Unless you want me to go through more of a certain topic, that's totally fine. Oh yeah, definitely at least one of each variant. Honestly, once you do a bunch of these, it's very repetitive. And again, I did all the heavy lifting, guys. All the answers are here. You're welcome. Someone wants to buy me a coffee, please. Just kidding. Yeah, so yeah, we'll just try to go through at least one of each. Because also, like, we don't need the session to go all the way to midnight. So anyway, we have actually 4 main rules here. We went through these already. The number of hosts is equal to 2 to the k minus 2. So remember, with the hosts, we minus the 2 broadcast and this IP hosts. The subnets themselves is 2 to the k. No subtraction is there. So you could think of it as the 2 things you have to subtract. These are hosts themselves, right? You could broadcast, or you could use just this IP, which is just the all zeros. So those would count as hosts. On the other hand, when we have to find the number of subnets or the number of hosts, right, we have to play around with the bits a little bit. So when given the number of subnets, go left to right. When given the number of hosts, go right to left. And I said sandwich the subway. Sandwich the subway. What am I saying? Too late for this. Sandwich the subnet bits. Okay. So I'm gonna be honest, the converting to binary, I think, was what I screwed up with most, because it got to a point where I literally could only see things in binary, and yeah, these kind of do take a while. So make sure you're good with converting things to binary, but once it is, then you're kind of good. Anyway, so when we go back to what we were talking about before with the cider, right? We see over here we have /24. This is referring that the first 24 bits are going to be your network ID, right? So this is going to be 8, 16, 24. These guys over here, your first 24 bits are your network ID. The rest of these guys are going to be your host bits, right? The thing is, though, right, we need to be able to create how many subnets? 4. So we're going to have to take pieces out of these host bits in order to actually create the subnets. And we know that our subnet for sure is going to be here, at least, but we're going to need a couple more bits for this. And the way we do this, right, is we know that the subnet formula is 2 to the k. So 2 to the k equals the number of subnets. Well, how many subnets do I need? 4. So 2 to the k equals 4. So that means k has to be 2, meaning we need 2 extra bits. These guys over here are going to be our subnet bits. So our total subnet is going to be all of this. Okay, now our net mask, right? Our net mask is going to have all ones in the places that our subnet is going to be. So that's basically going to be 26 ones. So what would look like this? Well, we know that if this is all ones, and this is all ones, and this is all ones, 255, 255, 255, but then our next 2 bits are also ones. So that's going to be 128 plus 64, 192. So this is going to be our net mask. And now what are the subnets that are created? I am really hoping that he doesn't give like a question with 16 subnets, because I'm not in the mood to be writing out 16 different combinations. You're going to be writing out all the combinations that you can make out of these subnets over here, and then I think probably converting them to binary. Not binary, converting them from binary to IP addresses, just to kind of probably be on the safe side. So over here, right, I know I could do 0, 0, 0, 1, 1, 0, or 1, 1. Remember, these are our subnets, not our hosts. So we don't have to worry about not having the 0, 0 or the 1, 1 as being like a bad address. These are our host bits, right? These are the ones that we need to worry about. That's why that whole formula over here. Now over here, right, what's the maximum number of hosts this time that can be attached to each IP subnet? Okay, well, what is our host bit? 1, 2, 3, 4, 5, 6. 6 total bits, each having 2 possibilities. Gee, I wonder, is there a formula for that? Right here, 2 to the k, so 2 to the 6, and then don't forget to minus the 2 for the 2 broadcasting hosts. So, exactly. Here. I just want to double check one thing with here. Okay, so it does seem that you would want to convert all of these guys to like the actual address. I'm assuming he would not give us something more than 4. There's a question with 16, and I'm just like, it would literally take the whole exam time to write out all 16 from binary into like numerical format. Yeah, so I mean, this is like the question from the exam, so you could kind of see it's like the same thing. How many bits would you use for your subnet ID? What is your net mask? What's the maximum number of hosts you need to connect? List all the IP addresses and calculate the subnet directed broadcast address, right? So in an example like this, right, this is the same, pretty much the same question. I'm assuming it'll probably look similar to this. because it is pretty much the same question. So again, we have 10, 10, 160, 0, 19. So our first 19 bits. 1, 2, 3, 4, 5, 6, 7, 8, I'm sorry, 8, 16, 17, 18, 19. So up to this point, we're the graded boxes, right? Then we need to do the 4 subnets just like last time. So the graded boxes, we have 26, not 26, sorry, 21, right? 19 plus those extra 2. And then if you were to just convert that, right, just kind of add up the powers, right? 128, 64, 32, 16, 8, right? Add it up and you get the 248. That's kind of how they got that. And then just like last time, these were the hosts created, so you could see that they made all the combinations. Pretty much the same exact thing in that case. And to calculate the subnet directed IP address, broadcast address. Yeah, subnet directed broadcast address. Right? This is just literally having it as all ones. This is like that one over here that we usually subtract out. And for this, you're literally just going to have everything after your subnet just have a 1. So you kind of have that. And then for this, I mean, you can kind of just convert this easily into from binary to this. It takes a little bit, but it's not too bad. All right, guys, what's going on? Where do you get the 26 bits of the subnet from? Yeah, so again, we knew it was 24 bits for your network ID, right? And then we also know that we have to set up 4 subnets. Well, how many bits do we need for that? We need k is equal to 2, 2 to the 2, to get 4 subnets total based on our formula. So 24 plus 2 is 26. So 26 is our total subnet bits. Yeah, y'all, I could just stop this review session, you know? Okay. So, yeah, I was just kind of also showing that this is pretty much the same type of question over here. You could kind of see their process as well. If this is a little bit easier to see as well, like with the whole how it's written and everything. Yeah, I think that's pretty good. All right, so let's maybe do another 1 or 2 of these guys, because this is definitely going to be on the exam, and then I'll just kind of skip the rest because it really gets repetitive after a while. So let's do this one over here, because why not? If you guys want to request one for the last one, go right ahead. Anyway, this time it's going to be /20. And that means that the first 20 bits is going to be our network ID. So, over here, we know we have 10, 10, 96, 0. Convert this guy to binary. The first 20 bits, so this is 8, 16, 17, 18, 19, 20. This is our network ID up to this point. But now we need enough extra bits to set up 16 subnets. So we put it into our formula again. 2 to the k equals 16. We know k has to be 4, because 2 to the 4 is 16. So 4 extra bits are going to have to be used for the subnet. So 1, 2, 3, 4, these guys. So that means 20 plus 4, 24 bits are for the subnet ID. So to get the net mask, we just make all ones in the first 24 bits. And this is actually really nice and easy to compute because this is literally just 255, 255, 255. So to compute the subnets themselves, I was literally not going to do the 16 permutations. I was not in the mood to write them out, but you could kind of see how the last one was. You could just kind of write them out. So like 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0. you get the picture. You could just kind of write out every type of combination between them. It's just these 4 bits that are going to be changing. And then converting them back to decimal. I think we're probably going to be allowed a calculator on the exam, I would believe, since we were allowed one on the last one. So I wouldn't worry too much about doing so many of these calculations, because I know it can get like really tiring after a while, so I wouldn't worry too much about that. Sorry, I just think the chat is really funny. Anyway, so over here, right now we have the maximum number of hosts. So the hosts are the remaining 8 bits. So that means we're going to have 2 to the 8 minus 2 is the formula. Okay. Is this the different one? Okay, yeah, this one's a little bit different. Let's do this one. So this time, we're given the number of hosts we want, but we are not given the number of subnets. So we want to find out how many subnets that we need in order to have 30 hosts. So this time we're going to have to work backwards. And this was the sandwich example that I was saying for the rule earlier. So over here, we have our IP. This is 10, 10, 212, 0. And 24 is going to be the number of bits that are going to be our network ID to start with. So over here, this part over here is going to be our network.
Sorry, can I ask something really quick?
Yeah, absolutely.
Are we always given the number of bits?
Yeah, you're always going to be given this /24.
Okay, thank you.
No problem. Yeah, so you're either going to also be given the number of hosts that you want or the number of subnets you want. And you're going to have to find the other one by yourself. So from that, right, we see we want 30 hosts. Okay, so how many bits do we need in order to make 30 hosts? Well, we can use the opposite of our formula, right? We know the number of hosts has to equal 30. So I could do 30 is equal to 2k minus 2 and solve for the number of bits that we need. Where was the question? Oh, right here, okay. So from that, right, we know that 2 to the k is equal to 30, right? 2 to the k minus 2 is equal to 30. We know that 2 to the 5 would give us 32. So that means 5 bits would be enough because I could do 2 to the 5, which is 32, minus 2, and boom, I have 30 hosts. So that's totally fine. So I'm going to use my last 5 bits for the host. So the host ID would be 5 bits. And for my subnet bits, right? Well, I said that there was going to be 24 bits from up here that was given. And then I know the last 5 are used for the host. So how many bits do I have for the actual subnet ID? I have 3 bits that were sandwiched in between. That means 24, these guys that were given from the question, plus the 3 sandwiched bits equals 27 subnet bits total. And which bits? What's your net mask? Okay, so net mask was the last thing we have to do. So net mask is these 27 bits. They're just going to be ones, right? And you can convert this into numbers as well. Okay, and then list the IP subnets created. How many subnets do you have? So from this, right, we know we have 3 bits over here. 2 to the 3, 2 to the k, right? So that means I have 8 total subnets. You can kind of get the combinations from that. I was just trying to get through as many of these possible, so I don't think he would give like a ton of them to write out, so I don't think it should be too crazy, but just kind of know how to solve for it. It's always going to be 2 to the k for the total subnets created. Okay. I think the rest of these are kind of straightforward. Till 7, I guess. They're all kind of the same. Does anyone have any requests to go over? Oh, how do you know that the net mask is 27 bits? Yeah, great question. So, we were given this /24 to start with. Meaning the first 24 bits, these guys, are going to be our network ID, right? This is like our subnet. But we need to know how many bits we can use for the subnet range itself, the subnet ID. And to do that, right, we need to see first how many bits are left over after we can reserve 30 hosts. Well, I know I need 5 bits to reserve 30 hosts, so how many bits are left? 3. So that means those 24 bits plus these 3 leftover bits, 27 is our subnet total. That kind of cleared up? Awesome. All right, so you could probably guarantee a question just like this to appear on the exam, just numbers switched up. So if you understand how I got these for both of these questions, then you're totally good. If you want to do more practice, we have all these questions here. I think he gave like, I don't know, like 5 or 6 of them. So like, go ahead, like just kind of keep doing them, and then you're kind of understand like the trick. But again, the rule, these are the main rules to keep in mind. So if you know these rules, you are good. When you're listing subnet IDs, you can just list any, like those 4 from the first question. Yeah, you're just doing all the combinations of them. So before, this was like only 4, so I just listed it out. But you are listing out the combination of these zeros and like these 2 bits here. So I could have 0, 0, 0, 1, 1, 0, 1, 1. These are the only 4 subnets that I can get out of this because I am only using those 2 bits for the subnet ID. So the entire subnet is this piece here, but the ID that kind of shows like what subnet it's a part of is these 2 bits over here. So when he asked the question, like the one that was saying 16 IPv4 addresses, I was not in the mood to find the combinations of these, so I just was like the 16 permutations of those 4 subnet bits. I don't think he'd give a question like that on the exam that has that much work involved. I think it would probably be only like between 4 and 8 subnets total, but you kind of get the picture of what's kind of going on, right? If I had these 4 bits, I could do 1, 0, 0, 0. I could do 1, 1, 0, 0. I could do 1, 0, 1, 0. You get the picture. It depends on the question though, so don't just like memorize a bunch of them. Like you actually want to find the combinations. So like if he asks for the number of combinations and you have 3 subnet bits, right? It's 2 to the 3. Or 4 subnet bits, 2 to the 4, based on that. So you want to be sure on how to actually get to the answer. That way you can, you could do that. But if you took like 241 probability or even discrete math, I think had a little bit of this, right? Finding the permutations. So that's kind of what you're doing here, right? 2 to the n, this time 2 to the k. Alrighty. Alright, 8 and yeah, 8 is a question that's a little bit different, so let's do this one over here. So we have two hosts, H1 and H2 are configured as follows. H1's IP address is this, and its net mask is this. H2's IP address is this, and its net mask is this. Okay. So what we have to do here, right, is we know that the net mask itself, right, if we were to bitwise AND the net mask and the address, I could get the subnet itself. So the question itself is asking, is it on the same subnet? So first things first, I need to know what the subnet is. So I do that by bitwising AND both of these guys. So H1's net mask and H1's address, H2's net mask and H2's address. And just a refresher, right? In this first position, there's a 1. In this first position, there's a 1. That means it's 1. There's a 1, there's a 1, it's a 1. But now it's a 1 and a 0. That's a 0. So that's how we're doing bitwise AND to get to our subnet. And you'll see, right, this is going to literally just get me the first 2 bytes. Because what is my net mask? The first 2 bytes. So these 1s are going to preserve exactly what's here. The rest of these guys are just 0 at this point. Because everything else here is 0, so we don't have to worry about that. So now I do the same for H2, right? H2 net mask, H2 address. I find the subnet. Now I can actually answer these questions. From H1's perspective, is H2 on the same IP subnet? Well, all I have to do is say, hey, is H2 on H1's subnet? And how do I do that? I bitwise AND them. So I bitwise H1 subnet, right? Because we're asked from H1's perspective, is it on the same IP subnet? So the same IP subnet is H1. And I'm seeing if H2's address is on this. So I just took the 2 numbers from that, right? That's H1 subnet, and that is H2's address. And you do bitwise AND, right? And the question is, do I get back the subnet? Yes, I do. And because I get back that subnet, I know that indeed H2's address is within H1's subnet. Now you're going to see on the part B, this is not going to be working, right? From H2's perspective, is H1 on the same IP subnet? So this time it's H2's subnet and H1's address. I'm going to bitwise AND these guys, and this time I get this number over here. This is not the same as this. Notice, this ends in 01, this ends in 00. This is not working. Because I did not get my subnet back, H1's subnet does not contain H2, right? We bitwise AND them, we don't get back H2's subnet. So that's how you do these questions. Right, and 9 is the same exact one. You find H1's address and net mask is given to you, bitwise AND them. You get yourself your subnet. If you want to skip the bitwise AND, a quick way of doing it is literally your net mask is going to be consecutive 1s up to a certain point. These consecutive 1s are going to keep this part of your address. So you know that this is going to match up with this and everything else is going to be 0. So that's kind of a quick way to do that. You still got to show your work, but you could kind of just show it like this and then quickly do it just like that and make it a little bit easier for yourself. So for this one over here, right, we find H1 and H2 subnet, and we say, are these 2 hosts on the same IP subnet? Show your work. Okay. So is our subnet the same? Yes, they are the same subnet. So we know that they're obviously on the same subnet, since they have the same subnet. Okay. Alright, before we go on to the next type of question, are we good on what we've gone through so far? Can you explain how you got the net mask? Yeah, absolutely. I know it could be a little confusing at first. Here we go. Okay. So, what's given to us? Each one's IP address is this. Its net mask is this. So I'm given H1's net mask and H1's address. I can bitwise add them and I get the subnet. And the same thing goes with H2, right? I'm given the IP address and the net mask. I bitwise add them and I get the subnet. So those two things are given to us. And again, for these questions, right, we take the subnet of whose perspective we're on and bitwise AND it with who we're seeing if they're on the same network. So it's like you're asking the host for their subnet and the client for their address. So let me know if that cleared it up.
Wait, can you go to the second problem again?
This
the
one?
one after this one. So I just had a question about the net max, like specifically. So I understand how you got all the ones at first, but how come like after the 8 ones, how come it isn't all ones as well?
Like over here?
After that, yeah, like after that dot, I guess.
Its net mask is 255. Oh, actually, wait. Yeah.
Sorry, that's why I don't know if like that was wrong or like right. That's why I was confused.
You know what? Let's do this one. Let's do this together then. Because this should be 1, 2, 3, 4, 5, 6, 7, 8. Okay, get rid of the 0. Okay, this is kind of. Whoa. Okay. Okay, and then this one should also be a 1. Why is this not working? Yeah, okay. So both of these have the same net mask, right? So I'm going to, wait, is this 1, 2, 3, 4, 6, 7 zeros? Okay. So I'm going to copy this over and put it over here. Okay. So I think this might still have the same answer because they have the same net mask, but let's just do this to be on the safe side, right? So we're going to bitwise AND these guys. So I'm going to just see, okay, I have all ones up to this point here. So this is the 8, 16, 17th bit. That means the first 17 bits of this guy is going to get preserved, right? Because if we were to bitwise add this, right, the 0 and the 1 make a 0. The 0 and the 1 make a 0. 0, 1, 0. 0, 1, 0, 1, 1 is a 1. So this is just literally preserving those bits. So 8, 16, 17. I'm going to just copy paste this, just save a little bit of time. Meaning that we're going to get this back as our answer for this subnet, right? And we do the same thing over here. Again, the same 17 bits. Oh wow, look at that. Still the same subnet. So I think I might have just forgot that part over there, so thank you so much for catching that. But it's the same process, right? So again, we convert our net masks into binary, do our bitwise AND to get our subnet. They're on the same subnet, so therefore they are, well, yeah, they have the same subnet, so they are on the same subnet. Okay. Any other questions about these? So with that being said, let's do this one over here. Question 10. Suppose a router has built up the routing forwarding table shown below. The router can deliver packets directly over interfaces 1 and 2, or it could forward packets to routers R1, R2. Describe what the router does with the packet addressed to each of the following destinations. You must justify your answer. Okay. So the key here, right, the rule in red, we want to bitwise AND the given addresses with each subnet mask to see if it equals the corresponding subnet IP. So quite literally, almost exactly what we were doing here, right? And if we get that subnet back, we have a match. We want to prioritize what's called the longest prefix, meaning the consecutive 1 pattern, right? That's given in our subnet mask, right? We see over here, these guys had 17 ones in their subnet. Now, these had the same net mask, but if let's say one had 17 ones and one had 18 ones, if they both matched, we'd prioritize the one with the higher number of ones, so the 18 ones. So if we take a look at each of these addresses, right? So all of these guys, I kind of took a bit of a shortcut here just because all 3 of these net masks, right, have a subnet of 255, 255, 255. So that means the first 3 bits are always going to be the same. And oh wow, look at that. 122, 15, 10. All of these have the first 3 bits are the same. So I'm only looking at the last byte. Because if I looked at the others, they're going to be exactly the same. So it doesn't really pay to look at them. Now you'll notice part E has a different subnet, and we'll get to why that one's going to be a special case later on. So we'll take a look at the first one, right? What I did for each of these was to start off, I converted all 3 of these guys into, the subnet. Yeah, we're bitwise on the given address with each subnet mask. Okay, so I took each of these subnet masks and I converted them into binary, right? So that's what I did over here. R1 is going to just give me back this. Our interface 2 is going to give me this, and interface 1 is going to give me this, right? So just to make things easier for myself, each of these 3 guys comes from here. I then take the last bit of the address itself that's given to me in part A. So that's 132. Converted to binary is this. Now I could go through each of these subnet masks, bitwise add them, and see what I get back. So first things first, I'm going to bitwise add my 132 with my first, which comes from R1. Okay, I get this, right? This would get me 128 if I were to convert it back. Now I have to see, does this match its corresponding subnet number? 122, 15, 10, my last byte is 0. Well, this is not 0. This is 128. This is not a match. Let's go to my next one. My next one comes from interface 2. So that's the 224 at the end that I converted into binary, right over here, right? So I bitwise add, again, my 132, and now my interface 1. And I get this. This is 128 again. Now I see, what is the last byte that I'm comparing to in its corresponding address? 96. Well, 96 is not equal to 128. Therefore, this is not a match. Now we'll see again on interface 1, we have over here the same calculation, right? Because the last byte is 224. I have over here, I'm going to take this, my 132, bitwise AND it with my 224, and I see, again, I get back 128. Oh, look at that. Now, interface 2's corresponding address has 128 at the end. That means that they match. So when I took my subnet mask and I bitwise added it with the address that I'm given, I only got back the subnet ID, which was this 128, on this case, meaning that interface 1 is the only one that it goes through. So this is a little bit of a confusing question at first, but once you do it a couple of times, you kind of understand the how it works. So let's take a look at the next one. Yeah, this is definitely going to be on the test, and don't worry, we'll take a break after we do these questions. So now we have our next address. This is B that we have. 122.15.10.108. So again, all of these have the same first 3 bytes. So I'm not even going to look at those. I'm just looking at my 108. So I'm going to take 108, convert it to binary. That's this bold over here. And again, I'm going to take the same 3 IP addresses that I had here to represent the 128, 224, and 224 that came from over here. And I'm going to do the same process. Bitwise add them. Okay, I do this with this and I get 0. Does this match the corresponding IP of 0? Yes, it does. So this could be a match. But we have to do the others because, again, we prioritize the longest prefix. The next one I do is interface 2, which had 224, which, again, we already converted that to binary, so we're good. Bitwise add that, and we get this. Does this match the 96? Yes, it does. This is 96 in binary, and this is 96. So this matches as well. We just have to still do the last one. And this, again, we bitwise add this. We already know from the last problem it's the same thing, so it's 96. And this last byte is 128, so this is not going to be a match, obviously. So we have 2 choices. Do we go through R1 or interface 2? So we have to see which one has a longer string of 1s. Well, this has 1, 1. This one has 3 1s. This is our longer string. That means we take interface 2, not R1. Does that make sense, by the way? I know this one's honestly probably one of the harder ones. But the trick kind of is just really seeing if it matches. We have a couple more examples, so we'll still go through those, of course. Over here, right, this time part C is going to be giving me 0.55. I'm converting this to binary. Bitwise add with the same 3 that I did. Okay, do it with the first one. I get back 0. What does the first one correspond with? 0. This means this is a match. Still, we got to do the others to just see. Bitwise add this. I get back this. This is 32, right? That's what that one is standing for. This does not match with 96. And we also know, again, this is the same one. That also definitely does not match with 128 either. So the only one that we did match with is this one over here. We must go through R1. Okay, good. It makes sense. Yeah, again, these are kind of tricky at first, but once you do them, then it kind of gets straightforward. All right, then we have D. This time, same process, 32. Boom. Do the bitwise add. This gets you 0, matches our first IP 0. This gets you 32. This does not match IP96. You have this, also 32. Does not match IP128. By default, you have to go through R1. And then lastly, our black sheep example, you could say. This one does not have a 10 here. Our subnets don't match. So even if I were to take this one, if I were to bitwise AND these guys immediately, it does not work. So because of that, it's not on the same subnet. I automatically send to the default router. So honestly, if you see these and you don't understand, if you take absolutely nothing from these questions, if you see one of these that does not have the same subnet, it goes to default. That's an easy 2 points probably. The others, you have to do the whole process that we did. But for part E, if you see that it's not the same subnet, boom, easy points. It's definitely not on your subnet, so you just send to the default router. Yep, exactly. Just listing the match and no match. So you're just doing bitwise AND. Let's do one more example of these and then let's take a break. So this time we are doing a different subnet, right? Notice all these guys, 255, 255, the first 2 bits this time, not the first 3 bits, are going to be the same. So before I go any further, immediately, who's the odd one out? This one is 1244. I don't even need to look at what comes after it. I know D is going to go to the default router immediately. So that's an easy 2 points. ABC, we're going to have to actually work out ourselves. So first things first, it's a good idea to start by converting all of your subnet masks to binary. These two are actually pretty easy to do. 128 is just going to be 1 with all zeros after. 192 is just going to be 1, 1 with all zeros after. These two were thankfully pretty easy. And if you notice, this time I'm doing 2 bytes. Because again, what does our subnet mask say? Up to the 2 bytes, they're the same. The 3rd and the 4th, that's when you got to check and you got to do bitwise AND about. Okay, so now we take the binary of our address. So that's 112, 100. Convert it to binary. Do bitwise AND. What do I get back? All zeros. My subnet has all zeros in it for those last 2 bytes. This matches. I bitwise AND with this guy. Again, it's the same thing. This one I know for a fact is not going to match with 128. Now I move on to the 192. I bitwise AND that. This gets me 128, 64. That does not match with 0, 0. And then again, 64 does not also match with 192. This is the only one that matches. What does this correspond to? R1. Move on to the next one. Convert 225, 48 to binary. That's this over here. We take bitwise AND. Take it with 128. We get 128 back. This does not match 0. Does it match with 128? Yes, it does. So this is a match. But again, we still have to do the others. Okay, do it with 192. We get 192 back. Does not match with 0. 192, get 192 back. Oh, look at that. It matches 192. All right, which one has a longer string of consecutive 1s? This has 1. This has 2. We take the 1 with the longer prefix. So it's the bottom one, which corresponds to interface 2. So interface 2 is the one that we choose. All right, and let's see as the last one, because again, this was the odd one out. Subnet does not match. You should really do the bitwise and, but at this point I was just like, okay, it just literally does not match, so don't even worry. Again, show your work for all of these. Yeah, just make sure you show your work. Don't just like say the answer is this because of this. Like show why it is that way. All right. So now both R2 and interface 2, I'm sorry, C, right? C is going to be 150, 92. I convert this guy to binary. Take the bitwise add with 128. I get back 128. This does not match IP0, but it does match IP 128, which corresponds to that. Bitwise AND with 192 does not match IP0, and again, does not match IP 192. So who matches with that second one? For 128, R2, so we send it to R2. Okay, and there's more questions on this. At this point, it gets extremely repetitive. There's nothing different really about this one, just the number of bytes that you're taking a look at. There is one that you'll actually see. It's possible for something like this to happen. It gets sent to the default router, not because it's not on the same subnet, straight up because nothing matches. So, like for this one over here, C is 128, 96, 40, 151. Okay, well, I know it's on the subnet, right? The only subnet that would work for it would be this third one, by the way, right? Because this is the only one that matches the 3 bytes as shown by the subnet mask. But if I were to take the bitwise AND of 151 and 0, right? Because again, 128, 96, 40, it's all the same. So I'm taking 151 and 0, right? And I do it with all of these guys, right? Actually, I don't even need to do it because these are not on the same subnet, not on the same subnet, not on the same subnet. This is the only one. It straight up does not even match the IP. So if you see that it's not on the same subnet as something, and if you do your bitwise AND, it straight up does not work, then you know you have a problem. So that is going to go immediately to the default router. None are going to match. And it's not on the same IP as anything else either. So that's the only other trick that I could think of, right? In a case like this where they give you a lot of different subnets that are very different from each other, make sure that you're only looking at the ones that apply. And yeah, it's possible that it just goes to default because straight up nothing matches. Okay. I think now would be a good time to take a break. So anyone have any questions before I pause the recording? Do we know which one router we are choosing? So the way we know which one we choose is, again, we take a look. First, we have to make sure the subnet matches, right? Then we take the bitwise AND to see if we take the bitwise AND of the address given with the subnet mask and we get the subnet number back, then it is indeed a match. And that's how we know we choose one of these guys to go to for the next hop. And of course, we choose, if there are multiple matches, then the one that has the more ones breaks the tie. So if we go through all A, B, C, D, and none matches with all, we put default. Exactly. So in this case over here, right? First things first, 1, 2, and 4 are straight up not on the same subnet. 3 is the only one on the same subnet. So that's the only one that I'm even going to bother doing bitwise AND for. So I do it, and I get 128, gives me 128. That does not match IP0, which is that last bit over there. So because of that, it straight up does not match the only thing that it's on the same subnet for. So it's just going to go to the default router. No problem. All right. You guys want to do a break or keep going? Are we asleep? I don't know about 30-minute break, but I could do 15. Yeah, because I'd like to get through these questions and go to bed, honestly. I have work tomorrow. Okay. 10 to 15 minutes? Okay, let's do that. So I'm going to stop the